Hello guys, in this video I am going to explain the electric field distribution, potential distribution and capacitance in the insulation of a cable. As you can see in the given figure, we have a conductor which is represented by the blue lines whose radius is Ri and it is surrounded by an insulation whose outer radius is Rho. Therefore, the thickness of the insulation is Rho minus Ri, as you can see here. This is the thickness of the insulation. In case of linear conductors, our charge distribution is considered as linear charge density, which is represented by rho L and whose units are coulomb per meter. And the total charge can therefore be calculated as rho L multiplied by the total length of the conductor. As you can see here, length is represented by L. Now, in such a cylindrical geometry, we can simply apply Gauss law to determine the electric field and potential. So, which is what we are going to apply. So, in order to apply Gauss law, we need to assume an arbitrary Gaussian surface. As you can see here, the Gaussian surface is assumed as another cylinder whose radius is R. This cylinder lies between the inner radius and the outer radius, between Ri and Ro, as it can be seen in the figure. So, if we assume this our Gaussian surface, we can take a differential surface area ds, and according to Gauss law, our electric flux is represented as E dot ds and integrated over the whole surface, and this is equal to total charge divided by the permittivity of this medium, epsilon. And if we integrate over the total surface area of this cylinder whose radius is R, then we will get the total area of this cylinder given by 2 pi R L, and this will be equal to Q over epsilon. And after rearranging this equation, we can get electric field equals to Q over 2 pi epsilon R L. Okay, so this is the electric field. As you can see from this expression, our electric field is inversely proportional to the radius of the surface, radius of the Gaussian surface. So, which means if we move away from the surface of the conductor, electric field will get weaker. Now, in order to determine the potential distribution in such an assembly, so the potential difference between inner radius to the outer radius can be represented by E dot dr and integrated over this radial distance from inner radius to the outer radius. Okay. So now we can put the value of electric field which we derived here. So this will give us Q over 2 pi epsilon RL and dr. So now in this case you can see only variable is R. Okay, rest of the everything is constant. Q is constant, 2 pi epsilon is constant, and L is constant. So we will take Q over 2 pi epsilon L out of the integration, and potential can further be derived by further solving this expression and taking the constants out of the integration, which are 2 pi epsilon L and integrating from Ri to Ro 1 over R dr. Okay, and by integrating and putting the limits, we will get Q over 2 pi epsilon L natural log of Ro over Ri. Okay, so now in this expression you can see that we have a similar relationship as electric field. Okay, now our electric field was Q over 2 pi epsilon RL, and here we have Q over 2 pi epsilon L. There is no R. So in order to find a relationship between the potential difference and the electric field, we are going to multiply and divide the this expression with R. Okay, so now we can see that Q over 2 pi epsilon LR is in fact our electric field, okay, as a function of R. Okay, so now we can say that, simply write the potential difference U equals to E multiplied with R and multiplied by Ro over Ri. Okay, and this is the relationship between voltage or potential difference and the electric field. And further, we can rearrange this equation to determine the relationship for E, which will be equal to U over R natural log of Ro over Ri. Okay, so this is another form of electric field. Here in equation 1, we had electric field in the form of charge, but generally we don't know the charge. In case of high voltage systems, we know the voltage of the cable, which is the potential difference between the center conductor and the outer surface of the insulation. So we know the potential difference voltage. Therefore, we can use this relationship rather to study the electric field distribution or to determine the electric field. Okay, now this relationship also demonstrates that the electric field is inversely proportional to the radial distance from the surface of the conductor. Therefore, the electric field will be maximum at the surface of the conductor. So E max will be equal to U over R now we are talking about the surface of the conductor. So R will be equal to Ri, and natural log of Rho over Ri, as they are constants. Okay, so this will be our maximum electric field, which will be occurring at the surface of the conductor. Now if we plot it, if we plot this electric field as a function of R, so from center to the outer radius to the inner radius of the conductor, our electric field will be 0. Why electric field will be 0? Because there is no electric field in the conductor itself, because there is no potential difference in the conductor itself. So if potential difference is 0, then electric field will be 0. So inside the conductor, everywhere our potential is same. So potential difference is 0 between inside the conductor. So electric field will be 0, and then electric field will be maximum at the inner radius. Okay, and then electric field will be varying, or it will decrease as a function of R. It is inversely proportional to R, and at this point our electric field will be maximum. Okay, now one more thing we need to determine, is capacitance. As you know that capacitance is equal to Q over the potential difference. Okay, so now we can rearrange this equation here. We can rearrange this equation here, which is a function of U and charge Q. If we rearrange this equation, we will get the capacitance equals to 2 pi epsilon L over natural log of Rho over Ri. Okay, so this was about the analyzing electric field distribution, potential distribution, and capacitance in a cylindrical insulation around a conductor, which is a practical cable case. Now, these two color density plots are representing the electric field distribution and potential distribution. As you can see here in this color density plot, the electric field is maximum. This red color represents the maximum or the higher value of electric field, and dark blue color represents the zero electric field, and the colors changing from red to light blue, they are representing the distribution of electric field or variation in electric field from maximum to the lower value as represented by the graph. So now here you can see at the surface of the conductor. So this is the cable. You can see this is the conductor, and at the surface we have maximum electric field, and then electric field varies outward. Electric field decreases outward from the surface of the conductor. And the second color density plot shown here representing the potential distribution. So potential is highest in the conductor, as you can see, and inside the conductor, as you can see, it is the same color. So all the points everywhere inside the conductor, they are at the same potential, And then when we move outward from the surface of the conductor to outward, then potential decreases. Now, when maximum electric field at the inner radius, as it is shown here, maximum electric field occurs at the inner radius or at the radius of the conductor itself. When it exceeds the dielectric strength of the insulation, then breakdown occurs, or we can say that material or the insulation near the surface of the conductor starts to degrade. Okay, starts to degrade. Okay, therefore, we need to design the insulation in such a way that at the inner radius, we need to make sure that the electric field does not increase the breakdown strength of the material of the insulation. If we consider the previous expression for the potential and the electric field, we can rewrite that expression, which was U equals to E R natural log of Rho over Ri. For the breakdown condition, we can write this one breakdown voltage, and we can write this breakdown strength, and maximum electric field occurs at the inner radius, so I can replace R as Ri. Okay, so now this is if we plot this equation. Okay, if we plot this equation as a function of Ri over Ro on the horizontal axis and the normalized value of this breakdown potential, breakdown voltage, normalized value of it over the maximum breakdown strength of the insulation or maximum breakdown voltage of the insulation, we get such a graph whose maximum value can reach, because this is a normalized value, so maximum value can reach to 1, and this maximum value can be achieved at Ri over Ro at a value of Ri over Ro 1 over epsilon. Can we design the insulation of a cylindrical cable? Then the cylindrical insulator is optimized to withstand the maximum breakdown voltage when the inner radius is equal to outer radius divided by O, which is actually achieved by rearranging this condition, that Ri over Ro is equal to 1 over epsilon. So if we rearrange this equation, we will get Ri is equal to Ro over epsilon. So this is the breakdown. So this expression will ensure us, if we select the dimensions of the insulation by satisfying this relationship, we will be ensuring that our breakdown strength will not be exceeded, or the maximum electric field near the surface of the conductor will still be less than the breakdown strength of the insulation. Okay, so this is all for today. Thank you.